Assalamu alaikum everyone. So lecture number 31, and we will be discussing PLAs and arithmetic logic unit, right? So let's start. So last lecture we discussed about ROMs, read-only memories, right? But they cannot have required efficiency, right? So the reason is that the decoder which we use during the RAM construction, right, it is actually generating all the minterms that are not being used, right? So in other words, you can say that no minimization is done, right? So that's why we can say that although potentially we can use that ROM, right, in an efficient and effective way, but we need to do something else, right? Or you can say that we have to perform some sort of simplification, right? So let's take an example, right? So here we have to implement a ROM, right? And there are n input functions, right? So what we need a decoder definitely for addressing, right? So the length of the decoder is 2 raised to power n, right? So what we are doing over here, right? We will be replacing that decoder with something else, right? So that's the place where we will try to achieve the required or potential efficiency, right? So what we will do, we will generate the minterms that are required, right? On the other side, if we are using decoder, right, it generate all the possible combinations or all the minterms, right, that even are not being used, right? So here what we have n inverters, right, and 2 raised to power n input n gates, right? And for the output, right, we need OR gate, right? So the number of gates roughly doubles for each additional input, right? So if I want to increase the length of the word within the ROM, right, so what I need to do, I have to double the number of gates. So this is very crucial point, right? Right, so here we have a blank, right? 3 into 4 into 3 PLA, right? So 3 mean we have 3 inputs, right? 4 mean we have 4 AND gates, right? And the length of the each word is 3, right? So you can see that we have 3 output and 3 OR gates, right? So this dotted part, right, is replaced for the decoder, which we want to avoid over here in order to have simplification, right? So you can see that here we have 3 inputs, right, and 4 AND gates, right? So this is the replacement of the decoder, right? So all the connections, right, you can see they can be made, right, to this AND gate. We have input as it is, and this is the inverted version of the same input, right? So here those inputs, they have to be ANDed via those AND gates, right? And then after that, those products, they have to be summed up, right? Right. So here is the simplification, right? So if I draw a truth table, right, what we need to do after the truth table, right? So for the simplification, we normally use K-map, right? So because in K-map simplification or minimization, we have to perform predefined number of steps, right? So we know the number of steps and the sequence, right? So first what we will be doing, we will be selecting the variables that has to be here, right, in this horizontal direction, and the variable that has to be placed in this vertical direction, right? So this is for V2. I go back, right? So here you can see that we have output, right? So let me mark the output, right? So I will be marking the output as, this is V2, this is V1, and this is V0, right? And here you can see we have V2, V1, right, and X, Y, Z, right? So I will go back, right, and I will be having X, Y, and Z, right? Right. So here you can see that we have this expression, right? So this is the main terms, right? So you can see summation, so 1, 2, 3, 4, right? So here we have taken YZ, right? So let me mark the M0, M1, right? So here we have a jump, M2, M3, right? So I will write here, so this is M4, M5, M6, and this is M7, right? So here you can see for this V2 we have 1, right? This is 1, right? And then we have 2, this is 2, and then we have 3 and 4, right? So now in the next step we have to perform the simplification, and for that we will be looking for the pairs, right? So here you can see that we have a pair in green, right? So this is another pair because we can reuse, right, the one in order to have as much simplification as we can, right? So this is the one, right, that has not been paired, so that is in red, right? So here we have the simplification. So again for V1, right, so you can see we have 2, let me write down M0, M1, this is M2, and this is M3, right? M4, M5, M6, and this is M7, right? So 2, right, this is 2, 6, where is 6? This is 6, and this is 7, right? So here you can see that we have this pair, right, and then this pair. This one has been reutilized, right? So we will have simplification over here, right? And then for V0 we have 4, right? 1, 2, 3, and this is 4, 5, 6, and this is 7, right? So this is 4, right, and 6 and 7, right? So here we have a pair. So after bending or flipping, right, so you can see that we have this pair, right? So we have, so now what is next, right? So now in the next step what we need to do, we need to write down the corresponding Boolean expressions, right? So you can see for V2, right, we have 3 expressions, right? So x, y bar, z bar, right? And here x bar, z, right? So x bar, y, z bar, right? Right, if I go back, right, so we have kept this pair, right? So we will see that why we have chosen this pair only and we are not using this pair, because this can also be paired with this, right? So we will see in a couple of moments why we have not paired this, right? So x y bar z, right? So x bar, so this is x, right, y bar and z bar, right, and this is x bar. For this pair, what we have x bar z, right, and for this we will be having x bar y z bar, right? And then let's move to v1, right? So this is the Boolean expression, right? This one, Boolean expression for v2. Now let's move to, again here we are only having one pair, right? So although we can have this simplification, right, so we are not using it, right? So here x bar y z bar, right? So this is the single one, so you can see that we don't have any minimization. So this is a term that consists of 3 literals, right? So here we have simplification, one literal has been simplified, right? So we are left with x y, right? Similarly, again here we are using this and this, right? So x y bar and z bar and plus there is another term, right? So as a result of this, right, so what we will be having, so this is y bar z bar, right, y bar z, right? So again jump 0 0 0 1 1 0, and here we have 1 1, right? So for this we have y z bar and this is y z, right? So for here z will be omitted, right, and we are left with x y, right? So again here we have x y, right? So here is the implementation, right? So you can see we have written the corresponding expression, and for v0 we have the xy, right? So here you can see that these are the inputs, right, starting from a2 a1 a0, right? So here you can see for v2, right? So for v2 we have x y bar z, right? So this is x y bar z, right? And this is what x bar z, right? So for this AND gate we have all the 3 literals, right? So you can see that this is this state, right? So no inversion. For this second one we have inversion, so that's why we have bar here. For this last one we have again inversion, right? And for this we have x y, right? So x, for this x no inversion, for y no inversion, right? So for x inversion, right? For z no inversion, right? And then we have inversion here for x, and inversion and no inversion for y, and for z it is inverted, right? So you can see the correspondence, right? So here in the rows we are performing ANDing, right? So you can see that this is they all being ANDed, right? So this is the output, right? But when we talk about the columns, right, so we have to perform the OR operation, right? So this one, right, so this is you can see that these are the switches, and that those switches they can be programmed, right? So we will have this one, right, and this one and this one, right? So it means x y bar z bar plus x bar z plus x bar y and z bar, right? So for this second v1, right, so we have x bar yz, right, x bar yz and xy, right? And here for this last v0 we have, right, x y bar z bar, right, and then x y, right. So that's the summary for ROM, right, because in the last lecture we have started ROMs, right, and now we are finishing it up or summing it up, right. So they provide stable storage for data, right, and for ROMs we need two elements basically, right. First one is the decoder that is used in order to generate addresses, right, and we can also model use those ROMs, right, in order to model melee and memory machine, right. So as I have mentioned in the previous lecture that ROMs are read-only, right, memories, but there are some specific and certain mechanisms. By using those mechanisms we can write the ROMs, right, but we have to be very, very careful, because if for example you are in the middle of the process of updating your ROM, right, and by chance the power failure occurs, and then it's very difficult to retrieve, right. So you have to do something else. You maybe have to do something that require physical maintenance, right. So then we mentioned that those ROMs, right, they have the potential of being used in an effective and efficient way, right, and in order to achieve that, what we need to do, right, we need to replace the decoder, right, and we call this configuration as PLAs, programmable logical arrays, right. So after having those different configurations, we can minimize the number of minterms that are being generated by using decoder, right. So if we have a ROM that includes decoder and the other circuitry, right, so we have to use generate all the minterms, despite the fact we are not using all of them, right. So in order to avoid that, we have replaced that decoder with a new configuration, and that configuration can be programmed. So that's why we call it a programmable logical array sort of configuration, right. So that's the summary for the ROM, right. So let's move to the other part, right. So we will be discussing about ALUs, arithmetic logical unit, right. So this is the main unit where most of the computation is performed, right. So we can perform different operations by using ALU, right. So these operations, they include add, we can add two words, right, or two numbers, right, and then we can add subtract two numbers. We can also perform certain logical operations, for example or, and, right, of two numbers, and we then will be having an example, right, an IC that have ALU, right. Then if we require or need a large ALU, right, so what we can do, we can cascade a number of ALUs, right. So we will see how we are cascading them, right. So in ALUs there are two very important factors that are involved. First is the data path, and then the control path, right. So we will be looking how we manipulate the data paths and control paths, right. So this is the symbolic representation of the ALU, right. So ALU, right, arithmetic logic unit, right. So we have input data A, this is input data B, and these are the functions and these are the conditions, and under those conditions the functions has to be processed, right? And this is the resultant, or you can say the data out, right? For example, if we have to perform the addition of two numbers, right? So first number has to be loaded here, then second has to be loaded here, right? So the condition may be that those two numbers has to be loaded, right? And then we will send the instruction that now we have to add those two numbers and store the resultant in some of the register or some of the. So here we have the operations, right, that can be performed: adder, subtractor, and AND operation, right? And this is the schematic for or IC for the ALU, right? So you can see we have different right inputs, right? So this is A's, A0, A1, A2, A3, and this is for B's, B0, B1, B2, B3, right? And this is the carry, right? But remember that this is the carry on the least significant bit position, right? And these are the switches, and those switches, they are actually the control switches, and those switches, they actually manipulate or mention different function types, right? This is the output, right? And this is the carry out, or you can say the carry in the most significant bit position, right? And this is the overflow, because there can be situation when we add two numbers, right, and we have overflow, and in that case this has to come into function, right? So this is the function table, right? So you can see we have three switches, so we will be having 8 different possible combinations, starting from 0, 0, 0, and then 0, 0, 1, 0, 1, 0, right, until 1, 1, 1, right? So you can see for 0, 0, 0 we have the operation clear, right? And it means all the data at the output has to be cleared, right? And then for 0, 0, 1, what we need to do, we will be actually performing B minus A, right? This is the operation name, right? And then for 0, 1, 0, A minus B, right? And here for 0, 1, 1, we will be adding two numbers, A plus B, right? And this is the exclusive OR, right? And this is OR, simple OR operation, right? For 1, 0, 1, we will be performing the OR operation. For 1, 1, 0, we will be having AND operation, right? And for all ones, we will be having preset, right? So preset mean all the output bits has to be 1, 1, 1, right? So in total we have 8 different functions, right? So that IC, ALU IC, it can perform 8 distinct operations or functions, right? So here we have an example, right? So we have 0, 1, 0, right? And this is the data that is available at the input, right? For this is for A's and this is for B's, and carry N, Cn, right? So it means the carry in the least significant bit position, right? And function code indicates, right, we have to subtract A, right, from B, so A minus B. So this is the resultant, right? And now we have changed the select code to 101, right? And we repeat the, right? So if I go back, so you can see that 101 is an OR operation, right? So now you can see that we are ORing two numbers, 1, right, 0, 1, and this is 0. So we can also synchronize ALU with the clock, right? So on the arrival of the clock edge, the functions has to be performed, right? So here is the extension of that ALU, right? So if I want to extend this ALU, right? So I can handle more number of bits, bigger numbers, right? The numbers that can have more number of bits, right? So obviously I need to extend that ALU, right? So here you can see we have B's, right, and A's, right? So if I talk about a byte, I want to add two numbers and each number is 1 byte, right? So 8 bits. So you can see starting from 0, 1, 2, 3, 4, 5, 6, 7, right? So these are 8 bits. Again here for A's, starting from 0 we have 8 bits, right? And similarly we are starting from for output F0, F1, F2, F3, right? So this is, you can see that 4, 5, 6, 7, right? So this is the carry, right? But this is the carry for the most significant bit, right? So you can see that the carry is propagating, right? So this is the carry at the most significant bit, right? And this carry is fetched over here, right? And these are the switches, right? So, and they are connected. You can have an idea why they are connected like this, right? So here you can see we have extended, right, the ALU, right? So it can handle 8 bits now, right? So what we have done, we have cascaded or connected two 4-bit ALUs, right? So as I have mentioned, if regarding the ALUs, two components are important, right? First one is the data path component and second is the control path component, right? So for data path components, there are certain components or elements that we can deploy. First one is the tri-state buffer, right? So here you can see that if enable is high, this input will be propagated to the output. Otherwise, when enable is low, it will act as an open switch, right? So this is the loadable register, right? So whenever we have load high, right, the data has to be loaded, right? And these are the two components that are being used for data path, right? So here we have the computation in a typical computer, right? So but here what we have mentioned, right, we have mentioned different components, like you can see control logic, this is data path, and these are the commands, and this is the feedback for conditions, right? So here this is the control logic, and control logic is normally implemented with the help of finite state machines, right? That include RAM, right? And the data path on the other side, they include ALUs, registers, tri-state buffers, and RAMs, right? So the ratio, right, is 5 to 1, right? Data path to the control logic, right? So it means data path, they are on the higher side, right? So how we can use or implement the data path, right? So consider the let's take the example. We have to add A and B and put the result in A, right? So first we will be loading A, right, and loading B, and then after that what we need to do, we need to send the instruction to the ALU that now the data has been loaded, and then this ALU will add them, right, and then finally the resultant is stored here at A, right? So then subtract A, B, and put result in B, right? So now we have to subtract those two numbers and put the result in B, right? And thirdly, right, we have to perform an OR operation, right, over the contents that are available at A and B, right? So here you can see that we have the data path utilization, right? So load and then this function, and you can see the lines, right? So now if we want to model the control as a state machine, right? So again we are taking this same example, right? So we have 3 steps. First we need to add A and B and put the result in A, and then secondly subtract A and B and put the result in B, and then we have to perform the OR operation between the over the contents that are available at A and B, and after that we have to put the resultant in A, right? So here you can see that we have S0, right? And next one is S1, right? So this is, you can say, this state, and this is S0, S1, this is S2, right? And here if we want to repeat, right, starting from step 1, so what we need to do, we need to move from here to here, right? So this is repeat starting from step 1. If I go back, right, so here you can see that repeat starting from step 1. So again here we have loop, right? So here again you can see that this is sort of feedback in order to obey this repeat starting from step 1, right? So now I'm here at S0, that represent add A, B and put the result in A, right? So here I have the function table, right? So you can see that I have to represent those same instructions, right? Because in computer we talk about binaries, right? We don't, computer cannot understand those instructions, right? It can only understand zeros and ones, right? So I have to convert those instructions into zeros and ones, right? So here you can see these are the states, right? S0, go back, S0 0 0, S1 0 1, S2 1 0, right? So this is present state, right? And this is the next state. So if I go back, so this is the present state, and this is the next state, right? So 0 0 and 0 1, and this is the present state, and this is the next state, right? So 0 1, right? So 1 0, and from 1 0 I have to go back. So this is the only path I have, right? So here from 1 0 I will be having next state 0 0, right? So these are the functions 0 1 1, right? 0 1 0, right? 1 0 1, right? So you can see that these are the functions, and whenever I will be loading, right, A, this is 1 0 0 1 1 0, right? So if I take this as a complete word, right, so let's move to the next slide, right, next slide. So here you can see that we have different colors, right? So this color is for function, and this is for next state, right? And this is for the present state, right? So now we have the instructions in ones and zeros, right? So that the computer can understand, and these are the instructions we normally have in our ROM, right? Read-only memory. This is the second word, right? And it includes the next state, function, right? And this is the loading of A and B, right? So we have combined them, right? So 0 1, right? So for this 0 0, 1 0 1 and 1 0, right? So you can see that each line or each row is having all the instructions that are required in order to perform the operation, right? So if I go back, right, so you can see that we have instruction for all the components that are involved over here, right? But we are using a ROM, right? Similar is the case whenever we talk about the ROM. So our ROM have those sort of instructions, and they are pre-stored, pre-written, right? So here we have put the control and the data path all together, right? So you can see we have the control, right, and then we have the data path, right? So control is being provided by those set of instructions, and these are the data paths, right? So you can see that we have different lines, right, and different feedback is also available here, right? So this is the next state and this is the present state, right? So we can have an idea, right? So here what we did, right, we have replaced that ROM with RAM, right? So we have the same set of instructions, but they are now in RAM, right? So normally whenever we load a program from the hard disk, right, so that program is loaded into the RAM, right, and then from RAM the instructions are being fetched and we are performing certain operations or functions and so on and so forth, right? So it looks like a software, right? So now you can see that we are actually having the software, and the rest of the data path is the same, right? So you can see we have present state, next state, this is loading, right, and this is the loop, right, feedback loop, right? So that's all for ALU, right? And today we have discussed PLAs, right? And we mentioned that by having PLAs we can have simplification, right? So if we talk about the ROMs, right, so we need to use decoder in order to have addressing, right? But the problem with the decoder is that it generate all the possible minterms, right? Even we are not using those all minterms, right? So in order to achieve the simplification, or in order to have minimization, what we need to do, we need to have a programmable logical arrays, right? So after the implementation we have taken the example of a certain configuration where we have shown that we don't have to use all the minterms. We will be deploying or having the minterms that are required for a particular configuration, right? And we have performed and shown the simplification and how we achieve the simplification, and after the simplification how we convert that Boolean functions into the real PLA, right? So then we talked about ALU, that is the main computation unit for a computer system, right? And we also talked about the data paths and control paths that are the essential and important components for the ALU, right? And then we talked about the extension of ALU, how we can extend the ALU, right? If, for example, we have a single ALU that can perform operation on 4-bit numbers, right? And we want to extend the length of the number, for example, from 4 to 8 or 1 byte number. So what we need to do, we need to connect different ALUs, right, in such a way that we can have the extension in the length of the number, right? And then finally we have model the ALU, right, by using the state machine, right, and included the data path and the control path, right? And we have taken an example, and then we introduced the ROM and the RAM within that model, right? So that's all regarding the ALU, right? So let's move to the other part of this lecture, right? So whenever we talk about digital logic design, right, so we need to design certain circuitry, right? But this is not possible physically all the time, right? So for example, if you have all the specification, right, the input, output and the functionality, and you want to test that idea or that specification, right, by designing the circuit, right, what you can do, you can have a piece of paper and pen, and you can draw the circuit, right? So sometimes it's difficult to do that, right? Because there are a lot of different combinations and a lot of different scenarios which you cannot test all the time and all together, right? So what we need a computer program or computer software, right? So instead of going into the lab and implementing the circuitry or the idea physically, and then after implementation you come to know, okay, that this there is some problem in the specification, or maybe there is some problem in the minimization, or there is some missing step in between when you start your design. So those sort of problems, they come across, right? So in order to avoid those problems, what we need a computer software or simulator, so that whenever we want to implement an idea, we simply can use computer, right? And over that computer we have the desired and required software, and we can implement the idea over the computer by using the software, right? So we have a number of choices regarding the simulation, right, for DLD digital logic design. So I have included 3 of them, right? So Circuit Maker 2000, right, it has a very rich library, right, and it is available for students, right? They offer student version, and student version is available on the VComSat's website, web portal, right? The other choice is Multisim, right, and the electronic workbench, right? So as I have mentioned that Circuit Maker, they offer student version, so we will be using the Circuit Maker, right? So let's talk about and have an idea regarding the Circuit Maker, that how it works and how we will be using in our course, right? So this is the snapshot of the workspace, right, of Circuit Maker, right? So you can see that we have different bars and panels, right? So here we have, this is the title bar, right, and this is the toolbar. Most of the tools, they are available here, right? So you can see that we have a bundle of tools that are available here. So this is the panel, right? So where you can see that we have different values, right? So if I select one component, so that panel will be activated and we can have different values, right? And then this is the schematic window. In white we have the schematic window where the actual circuits are being drawn, right? So ultimately after the drawing, right, and after all the connections and all the configurations, what we need to do, we obviously want to analyze that circuitry, right? So for analysis, right, we have a different window, right? So there is a split, right? So that is the schematic window and that is the analysis window, right? So here we have the status bar and this is the analysis tab, right? So as this is a very generic software and it offer AC analysis, right, DC analysis, and operating point and transient analysis, right? So but our focus whenever we will be using Circuit Maker will be the digital logic design, right? And this is the probe tool. That is very important tool, right? So if I want to check that or I declared certain test points where I want to check the voltage or the output or some other parameter, right? So I will be probing this, right, using this tool, and I will be probing that test point, right? So this is a brief introduction about the Circuit Maker workspace, right? And then there is another important feature, that is connectivity, right? So obviously we have different components, we have different libraries, and whenever we put a component, right, in this schematic window, right. So what we need to connect them, right. So for connection, we have another tool, right. So that is the connection tool, right. So that is very, very important, right. So whenever we connect two components, right, so the there has to be something on the back end of this software that should be stored, right. So that is actually exported or stored in netlist, right. So and that is stored in the Rex maker, right. And we have different sections in circuit maker, right. Schematic window, right, and the analysis window and the panel, right. So I have already discussed those, right. So this is the schematic window and this is the panel window, and then we have the analysis window, right. So this is the analysis window, right. So where we actually draw the circuitry, right, and then one circuit file at a time can be opened. So this is you can say the limitation, right. So you can only open one file. So it's not like other softwares, right, where you can open multiple files. So here we have a limitation that we can only open one file, right. So the analysis window, it includes the simulation results, right. So obviously you have to simulate or run the circuit, so the results has to be displayed. So for that, analysis window is the place where we will be looking for the results, right. So panel tab, it's used to select control which are relevant to available, right, displays, right. And then here we have the schematic, right. So you can see we have this is the operational amplifier, this is the resistor, and so on and so forth. But we are focusing on digital logic design, that includes the basic gates and or not, flip-flops, right, and different ICs. So in ICs are also available, right. So the ICs which we have studied so far, they are almost available in the libraries, right. So you can see that we can draw different schematics, right. So here this is the device symbol, right. So if I have to explain this, right, and this is the ground, and here we have the label value, right. We can change the value, and this is the designation, right, and this is the label, nodal label, right. So there are a few conventions, right, which we have to follow. All the files, all the schematic files, they are being stored with the extension .ckt, right. And then obviously we have library, right, and their classifications, and for that we have .dat file, right. And the device libraries, right, they are being stored with the extension .lib, right. And then we have certain model files, and they are available with an extension .mod, right. So we can also have a sub-circuit file with the extension .sub, right. For example, you have a very huge circuit, right. So you can see that within that schematic window we have a limited place, right. So we can there can be a scenario where all the components, they are not being drawn over here, right. So what you can do, you can design a smaller circuit or sub-circuit, and you can save that file, and then you can call the same sub-file into your main file, right. But you need to follow certain number of steps, right. And then we have waveform display, setup files, right. And this is the toolbar, right. So we have the panel, and these are the very conventional sort of tools: open, save, print, and this is the arrow tool, right, and this is the wire tool, right. So this is the wire tool. If we want to connect two components, so this is the tool which we need, and this is the text. This is delete tool, probe tool, zoom, right, and rotate if you want to rotate a component, and then this is the tracks maker, right, and this is reset, analysis setup, analog, right, trace digital if you want to trace digitally, and then step digital, right, and this is reset, run digital, and these are the tile windows, right. And we have a very rich library within the circuit maker, right, so we can browse, we can also search different components. If you remember or know the name of a certain component, so you can search there, right. So here you can see that these are the active components, and we have NP and transistor, right, and this is the number, model number, and this is the description, right. So you can browse, search different components, right. Okay, so placing, right, so we have to double click on a certain component, right. So this is a sort of drag and drop, right, like there are certain softwares where you can simply drag and drop different components and different, right. So these are how we place, and this is the properties, right, and you can go into the properties, and these are different fields with combo boxes, and you can change values, right. So here you can see we have device, right, this is sort of voltage source, this is the labeled value, designation, right, and you can have different combo boxes, right, and check boxes, right. So if you want to make it visible, this is checked by default, right, so you can also have invisible component, and you need to select analog and digital, right, whatever you want, right. So wiring it together, all these components in order to make a circuit. So these are the steps we have to go through, right. So let's take a few examples, right. So in order to have some, so it is here, right. So you can see that we have utility, right, readme, that is help file, and this is the exe file, right, and this is the tracks maker, right, tracks cam and tracks maker, right. So we will be loading the circuit maker, right. So the best way to grab this software in a quick and efficient way is to look for examples, right, to start from examples, right. So you can see this is the schematic window, right, and these are the tools, right, that are available, right. So here you can see that we have this is the folder where circuit maker 2000 is normally installed, right. So you can select the path, right. So this is the default path, right. So it actually in program files, right. So circuit maker examples, we have different folders, right, library, models, PCB template, and track scam, right. So I will be going for examples, right. So let's talk about, so this is a 555 timer IC, right. So you can see that we have an integrated circuit, and how I can run the simulation, right. So here you can see I have run the simulation, right. So this is the probe tool, right, this is the oscilloscope, right. So you can see that a very precise clock, right. So this timer IC is used in order to generate a clock signal, right. So you can calculate the frequency of that clock, right. So here you can see if I want to check this, right, so this is the point where this clock is available, right. So I want to check this, this is grounded, right, and here you can see that we have this signal, right. It is refining, and here we have the A, right? Right, so you can have different, right? So here we have, right? So this is the, right? So this is a sort of charging, right? Okay, so let's have, right? So I can only open one file, right? So we will be having a very simple, so what I can have, right, gates, right? So I want to show you, this is an AND gate, right? Right, so I have this logic display, right? So let me place 2, right? And then I have to browse the power supply, right? This is the power, and so this is power supply, right? And power supply, right? So next, these are the components I will be using, right? So next I have to connect them, right? So this is the connection to, again, right? And here I have, right? So I need in an inverter, right? So here I am, what I can have, right? And I will be having this, right? So here we have an AND gate, right? And these are the logic displays, right? So now I will be running that. So what error? So what I can have, I can delete this, right? In order to have, right? So let me see, digital mode, right? So here you can see that now it's working because we were not selecting the mode properly, right? So 1 1, and this is glowing, it means output is 1. See, if I want to verify, right? So this is high, and this is high, right? So let's have another. So I stop this, right? Browse, and I will be having, right? So I will be having another. So Control D, right? So here I have this, and then I will be having an inverter, right? So right, and joining this, right? And now let me run, right? So this is 1. After the inversion we have 0, right? So if I probe, right, so here we have high and here we have low, right? So you can see the high and low, right? So this is high and this is low, this is high, high, right? So I can have another ground, right? So I will be applying, right? So this is ground symbol, right? So I will be applying. So let me delete this, right, and rejoin this, right? So this is the connection, and now we are analyzing this, right? So you can see that we have 1, this is 1, this is 0, and here we have right, 0, and after this inversion we have a 1 over here, right? So let me verify this. This is high, this is low, this is low, right, because this is an AND gate, right, and this is not glowing, right? So we have low, low, right, low, and this is high because after the inversion we have a high here, and this is glowing, right? So this is a way out, right, of designing and performing simulation, right? We can stop and we can also have analysis, right? So let's open more examples, right? So let's talk about 741, right? So we are not saving, right? So this is, right, so let me try for some. So this is an A stable, right? Again, analog components are there, right? So let's talk about or look for. So this is a counter, right? So you can see that, right? So this is a counter. We have already studied a counter, right? That can count up and down, right? So we can also load data, right? So this is this should be a countdown, right? So right, so this is these are the switches. You know, we have switches, and this is count enable, and this is the IC actually, right? So we can also load another example, right? Right, so this is the circuitry, right? So what we can have, we can start, right, and you can see that these are the counters, right? Stop, right? And in order to have the reset, right? So this is the reset, right? So this is a sort of full-fledged solution, right? So this is for red car, green car, and blue car, right? So we can calculate, right, and we can, right? So this is a sort of circuit, right? So what it is doing, it is computing the time the cars are taking in order to reach the destination, right? Right. Right. So that's all regarding the circuit maker, right? Right. So we have discussed a simulator that can be used in order to simulate different circuits, right? The problem, especially when you are studying remotely, right? So it's not possible to go all the way or all the time into labs, right? So in order to overcome this difficulty, you can have what you can have. You can have a computer, and you can also have the student version of this circuit maker simulator, right? And you can define your idea, or you can have an idea on a piece of paper, right? And for the implementation, right, you can just use the software, and after designing or after constructing your circuit, right, into the while using that software, you can simply analyze your circuitry and your design and verify either it's correct or incorrect, working properly or not, right? So that's all for today's lecture, right? So I hope you will be performing simulations, right? What we have studied so far, like you can design an adder circuit, right? A half adder. You can start from the simple circuit by designing a half adder that can only add 2 bits, right? So and then you can move on to the complicated circuits, right? So that's all. अपना ख्याल रखिएगा. अस्सलाम वालेकुम.